Welcome. We are trying to look at the optimization of a functional, and let us consider a functional which is like this: I is equal to integral x1 to x2 f of x y y prime, which is nothing but dy by dx dx. This is the functional which I want to optimize, which I want to extremize. Now, like in usual in mathematics, we know if we have a function which is dependent on one variable, how to extremize. We know what is the necessary condition. So, I mean, we are going to pose this problem in the same fashion, so that we can actually also solve this problem. For doing that, in the case of a function where we were trying to find out where the extremum point is, we first assume that there is a point A where the function actually achieves extremum. In this case, I am going to assume that there is some y of x, which is a curve or a function or path, whatever you want to call, for which this is y of x which extremizes I. So, I am going to assume this is equivalent to assuming that A is the point where f of x had a extrema. So, like that I am going to assume that y of x is the point where if you choose that path, this I is going to be extremized. So, that is the first thing. Now, like we said that about A you have to choose points x within an admissible range, I am going to define an admissible set of functions which I will look at to find out how to optimize this. How do I define that admissible functions? I define them as y tilde of x as nothing but y of x plus epsilon some eta of x. So, these are admissible functions. So, I am going to choose some functions which are admissible functions. How do I define? They are the extremizing function plus some scalar parameter epsilon multiplying some other function eta of x. So, what is it that we are saying? Suppose I am in the x y space, then y of x is a curve like that. So, this is y of x and this is point x1 and this is point x2. By this I am choosing different functions. So, I am choosing functions like this. So, each one is by epsilon and some eta, but all of these eta are going through points x1 and x2, which means eta of x1 and eta of x2, right. So, the so called variations, right, how different are these from y of x? They are not different. So, I am going to assume that they are 0. Etas are functions such that because they become 0, irrespective of what epsilon you use, you are going to get y of x1 and y of x2 at those points. That is what that achieves. And now epsilon, by choosing different epsilon, you will get to different functions. So, this is and I am also going to assume that etas and y's are all differentiable as many number of times as you would need them to differentiate. So, let us assume that that is given. Now, let us consider the varied functional. What is the varied functional? Let me call it as some I tilde. I tilde is the functional which I consider between the same x1 and x2 with f, x does not change, y tilde and y tilde prime dx. Now, when epsilon becomes 0, the admissible function actually becomes the extremizing function. So, epsilon equal to 0 is the place where my admissible function actually reduces to the extremizing function. Okay. So, let us remember that. So, we write this f of x y prime y tilde and y tilde prime, which is I tilde, and let us look at what happens to this I tilde. Okay. So, I tilde then is equal to integral f of x y tilde y prime tilde dx. But we know y tilde and y prime tilde are nothing but f x y plus epsilon eta comma y prime, that is nothing but y prime tilde nothing but epsilon eta prime, then dx. So, now let us look at this I tilde. If I look at I tilde as some quantity, so which is I tilde at epsilon equal to 0, that is the for the optimizing function I tilde, that will become I itself, plus d I tilde by d epsilon, where epsilon equal to 0 times epsilon, plus d squared I tilde by d epsilon squared at epsilon equal to 0, epsilon squared by 2 plus etc. What is this? This is nothing but the Taylor series expansion for this, because now it is dependent on only this epsilon. So, in terms of epsilon I can actually Taylor expand for I tilde. Now, I tilde when epsilon equal to 0 is nothing but I. So, I tilde minus I, which is nothing but what is known as the variational of I, is equal to d I tilde by d epsilon at epsilon equal to 0 epsilon plus d squared I tilde by d epsilon squared by 2 factorial plus etc. Now, we know that the necessary condition for an extremum to be achieved is that d I tilde by d epsilon at epsilon equal to 0 should be 0, d I tilde by d epsilon at epsilon equal to 0 should be 0. So, this is the necessary condition. So, what did we do? We took the functional, we varied it a little bit, and the variation was defined completely in terms of a scalar parameter. So, we could go back to some f of x, one parameter function, for which we know what is the necessary condition for optimization, and now we are implementing that necessary condition on this functional. So, what is d I tilde by d epsilon at epsilon equal to 0 for this function? So, let us write that down. So, that is nothing but integral x1 to x2 dou f by dou y tilde dy tilde by d epsilon plus dou f by dou y tilde prime dy tilde prime by d epsilon dx, all of which is evaluated at epsilon equal to 0, that is equal to 0. So, this is what we have found as the condition. Now, when epsilon equal to 0, you can see that y tilde will become y itself, and so you will get integral x1 x2 dou f by dou y, and because epsilon is 0, dy tilde by d epsilon, which will become just eta. Similarly, y tilde prime will become, when epsilon is 0, dou f by dou y prime, and this will be eta prime dx, that should be equal to 0, right. So, we have implemented the condition that epsilon should be equal to 0 at the for the extremum. I mean, this has to be evaluated at epsilon equal to 0, and that gives me this function. Now, eta prime is nothing but d eta by dx. So, I can do an integration by parts, and that gets me to the point x1 x2 dou f by dou y times eta. If I take d by dx and put it here on top on in front of this, so I get d by dx of dou f by dou y prime times eta integral dx. There is an extra term, so it is v dx, so it will be v u dv which will be u v evaluated at the extreme points minus v du. So, that is how we got this. So, there is that other term, so which is dou f, so plus dou f by dou y prime and eta, which is evaluated at the points x 1 and x 2. So, this is the excess term that is coming because of the integration by parts. Now, we assumed that eta at both x 1 and x 2 is 0. So, because of that this goes to 0, because we assumed that there is no variation at the points x 1 and x 2. Notice that I can also choose functions for which eta of x 1, eta of x 2 might not be 0, as long as dou f by dou y prime is 0 at these 2 points, I can still satisfy this condition. So, we assumed one condition, but this is not the only condition in which this term will go to 0. In any case, you can make it go to 0 either by assuming the variations which are consistent with the endpoints, the eta becoming 0, or dou f by dou y prime becoming 0 at the endpoint. So, either way you can do it, you end up with this. So, let us write that in a slightly simplified fashion. So, we get this x 1 to x 2 dou f by dou y minus d by dx of dou f by dou y prime, everything multiplying eta dx is equal to 0. Now, eta is an arbitrary function, right. If you have an integral x 1 to x 2 multiplying some arbitrary function is equal to 0, then it necessarily means that this integrand should be 0. Suppose if it is not 0, if it becomes non-zero even if at one single point, because I have the freedom to choose eta arbitrarily, I can choose eta to be a delta function, a function which will peak only at that point, will be 0 everywhere else. So, this integral will become non-zero. So, it is not allowed for this integrand to be non-zero even at a single point in this domain. It has to be necessarily equal to 0 over this entire domain. This is known as the Euler-Lagrange equation. From the derivation, it is clear that Euler-Lagrange equation is nothing but the necessary condition for a functional to have an extremum. Why? Because that is how we derived this Euler-Lagrange equation. We took the functional, we demanded that it should have an extremum at some point, and we posed it as a problem with one single variable. So, we used our usual Taylor series expansion trick, and we know what is the necessary condition is. That necessary condition led to this condition. So, Euler-Lagrange equation in the case of a functional, it is a condition on the variational derivative that it should obey certain equation for that function to have an extremum. So, this is known as the Euler-Lagrange equation. Of course, to prove that this extremum that you have achieved is a minima or maxima, you have to look at the second variation. And in general, it can be done, and it is a little bit complicated. Not many material science textbooks I have seen where the second variation is done. An exception is an excellent textbook by Kachaturian on structural phase transformations. He does both the first variation and second variation, but in most of the cases, because the functional that we would write is a physically motivated functional. For example, it is something like action, or it is something like free energy, or it is something like an entropy. These functionals we already know whether they get minimized or maximized, right. In physically meaningful situations, these functions are going to be, free energy for example is always going to be minimized. So, if the problem is posed thermodynamically correctly, then that functional automatically, if it reaches an extremum, I know what type of extremum it is. So, most of the times we do not worry about the second variation or looking at the next condition, which is the sufficiency condition, but the necessary condition is the so called Euler-Lagrange equation. This is for the function to achieve its extremum. Okay. In most of the physical cases, the extremum, that extremum is basically the equilibrium state. So, this is also the condition. For example, if you are taking a free energy, functional, and if you are doing Euler-Lagrange equation, the solution you get basically tells you that that is the condition for that free energy to be minimized. So, at the equilibrium when the free energy is minimized, that is what will be achieved in that particular system. So, that is what it means. So, what we have seen is the definition of a functional, how they naturally arise. There are many problems in which functionals of this type come about, and using some Taylor series expansion based ideas about minimization or maximization of single variable functions, you can extend it to the case of functionals, and you can derive an expression which tells for a functional to be extremized what is the condition that has to be satisfied. That condition is known as the Euler-Lagrange equation, which is what we have derived in this part. So, this is one of the important pieces apart from group theory and symmetry when we want to look at phase field models. Okay. So, this is known as variational calculus. So, writing functionals and taking variational derivatives on them is one of the important aspects of the phase field formulation. So, we will look at a little bit more of details about variations in the next lecture. Thank you.